This is video 11.4.1, and the goal here is to know how to find the slope of the tangent line, or the instantaneous velocity. Those are equal statements at a given point of a function. So we want to know how fast is something moving at a certain point. What's the slope at that particular moment? So remember, we talked about this problem with the kid growing. This secant line, this purple line that cuts through these 2 points, would help us find the average rate of growth from the age of 13 to the age of 18. And that's the math that we're doing up top here, because he grew 19 inches in 5 years, which averages out to 3 inches and 4/5 of an inch every year. And that would help us see how he grew from 13 to 18. But remember, what we noticed is there's different changes in rate. He's hardly growing right here. Here he grows a lot, and then here he slows down. So that's not a very good description. So we talked about how we wanted to find the instant rate. What happens at that exact instant in that graph? What's happening right at this exact moment? Or what's happening here at that moment? How fast is he growing at that moment? Now that's what we're going to talk about next, because first let's understand how we found that rate in general. So the rate between any 2 points, P and Q, is the difference in the y's divided by the difference in the x's. Because we would look and see how much did we grow in how much time. Usually x is time and y is the inches or the feet, or maybe it's the money. How much money per foot did we grow? So the growth is a slope equation because it's the rise or the run. How much did we grow in how much time? And so it can be calculated by using this formula that you see here, which nicely simplifies to the difference of the functions all over h. But we want to narrow in. Remember, we don't just want from P to Q. We don't want an average rate. We want to narrow in and get as close as we can to P if we're asking the question, what's the instant growth rate at exactly P? What is the instant growth rate? And the next picture helps us see how that's different. So here's a description showing what happens as we get closer to P. This is the first Q, and we have a secant line. If we were finding the average growth, it would be extremely different than if we went from this P to Q, because this is my slope triangle on that one. My slope triangle on the original Q, is much steeper. So those are very different descriptions of the growth. They're both averages. But what happens as we get extremely close? So what happens as we move closer and closer? Here is our closest point that you see on the graph. This is a much better description of the actual growth at that exact moment. So remember, we're getting a plus h, and we're getting it closer and closer to the actual value a. In the class lately, we've been talking about maybe 5, and this might have been 5.001. And we would get a really good description of the instantaneous velocity, but it wouldn't be the exact value. The formula for the exact value is described here. What we want to happen is we want to get really close. We want this triangle that I've been talking about to really be exactly at P, and we don't just want it to be a secant line that goes through 2 points. We actually want it to be this tangent line that only crosses at P, and that in fact never crosses the curve, the blue curve, ever again. So we want actually this h to turn into 0. We want the change to be nothing. We want to go from 5 to 5, not to 5.001, because that's not instantaneous. That has let some time pass by. So what we do is we use limits, and we use what we understand about limits to calculate that. And we find the limit of the slope formula as h gets really small. In fact, as h goes to 0. So that's the description, and this is the formula you want to write down. This is how you find the slope of a tangent line. It's also how you find the instantaneous velocity at a certain point A, okay, at this particular exact point, A comma f of A. When we want to know what happens at that point, we're going to use this formula to find the instantaneous rate of change of that function at A. So let's take a look at how that works. We're asked to find the slope of the tangent line to the graph f of x equals 2x squared plus 3 at the point -2. So the formula, let's first write down, is the limit as h goes to 0 It's the difference of the function f of a plus h minus f of a all over h. Now in our case, a is negative 2, because that's our input number. A is negative 2. So we're going to do negative 2 plus h for the first function, and we're going to plug in negative 2 to the function for this thing we'll subtract. Thankfully, we already know half of the answer here, this top part at least. F of negative 2 is 11, according to this point that they calculated for us here. So that point is 11. So we do need to calculate this. So off to the side, I'm going to calculate what the f of negative 2 plus h is. And this is where my algebra skills come in handy. I'm going to plug in negative 2 plus h in for x. And I'm going to work it out and simplify it. So I'm going to get 2 times, let's see, squaring this value, I'll get 4 minus 4h plus h squared plus 3. So my f of negative 2 plus h is, let's see, so it's still a limit as h goes to 0. But I'm going to replace this value with this. Let's see, let's distribute the 2, and then I'll write it out here. So 2 times 4 is 8, minus 8h plus 2h squared plus 3. And then I'm going to subtract 11, because that's the value of f of negative 2. And that's still all over h. H is still on the bottom, and I'm still taking the limit as h goes to 0. So now I'm just going to simplify things out and see where it takes me. So let's see, on the top I have 8 plus 3 minus 11, so that's really gone. Let's cancel it out. So I have negative 8h plus 2h squared all over h, and I'm still taking the limit as h goes to 0. So now I'm seeing where I'm headed. Remember, my goal is to plug in 0 when I can, when I don't get an error. And I see that I can factor the top so that the h's can cancel. H times negative 8 plus 2h all over h. Now the h's are gone, and my limit is simply plugging in 0 for h. And I get negative 8. So apparently the instantaneous velocity, the rate of change, the slope, all those things are the same. The slope of this function at negative 211 is negative 8. There's my answer. The slope is negative 8. Now if I look at the graph, I should see, number one, I know it's a parabola. So apparently at negative 2, it's up at 11, and apparently it's a negative slope. So it's something like this where it's negative. It's going downward there. I don't know if the rest of the graph is right, but it should be a negative slope if I were to draw a tangent line at that point. And that's one way you can kind of check your answer. It should kind of make sense with the graph that you have. It should be steep and it should be negative according to our answer here. So that's how you answer a simple question like that. Now when we get to some more complex ones, go back to our original problem that we talked about at the beginning of the year, beginning of the chapter, excuse me. We looked at this firework and we wanted to analyze how fast is the firework traveling at 6 seconds was the question. So we found 6 seconds, and we even found how high it was in the air at 6 seconds, and we looked at 7, and we looked at 5. Sorry, we looked at 6, 7, and 5, and we found those 3 key points. And we use that to kind of analyze and kind of figure out. Now, I don't remember what all those values are, but the good news is I don't need those values anymore. I can erase those and not worry about those. But taking a look at the question, if we want to find the instantaneous velocity at 6 seconds, that's really saying what's the slope at 6 seconds, the tangent, the slope of the tangent line. So here was our function that we had. I'm not going to go through how to get that again, but I'm going to use the formula. I'm going to use what I learned about finding this tangent slope. I'm going to ask what's the limit as h approaches 0 of f of a plus h minus f of a all over h. In this case, a is 6 because that's the question. It's asking me about 6 seconds. So I'm looking at f of 6 plus h and f of 6. So I'm going to plug in f of 6 plus h. I'm going to find out what that is by putting in 6 plus h in for x. And I'm going to simplify that out and see what I get. I'm also going to figure out what is the function at 6 seconds. So I'm going to plug in this. And then I'm going to plug those results. Into my formula. I'm going to plug them into my formula up here and simplify. And that, in fact, is your checkpoint. Your checkpoint is to finish this problem. Your checkpoint is to finish the problem and find these values and plug them back in and try to find the limit as h approaches 0 of this slope line. So finish out the work that we started here. Use your algebraic calculations and see if you can find the exact velocity. If you remember, we were talking about it being, I think it was about 9, but we had some kind of debates and we weren't sure if that was an exact number, if it was right or wrong. So do your best on solving that and bring your questions into class and we'll go over to start class tomorrow.